So my name is Eric Vetia. I'm a principal product manager for Java Card and looking also at all the embedded security topics at Oracle. So I will focus this presentation on security with really a specific focus on the edge devices and even further that into what secure elements in edge devices can bring in terms of security. Okay. So what we'll start with a little introduction about the specific requirements for embedded security. And for doing that, I'll try to illustrate it by examples from the utilities area with a smart meter use case to which a lot of people can actually relate fairly easily. And then we'll look at how we can build trust in several ways by using secure elements. And then we'll look at how Java Card and Java can work together on embedded devices and conclude in a few final statement on the edge to enterprise security. So let's start by setting the scene here. So we're on something very classical in terms of deployment of devices. So we look at systems in which we have an enterprise application which is made of backend, some storage. Maybe it's in the cloud, maybe not. That's not really the main topic here, since we'll be looking at the other side of the end-to-end thing. And then we have connected many devices. So these devices can be of any kind. They can be very small, like sensors. They can be very large, embedded devices, like multi-million-dollar machine used in a hospital. The important thing here is that these devices, they have an existence by themselves. They are not just made like computer or tablet just to interact from a user with a backend. They are meant to work by themselves. In most cases, I think a wide majority of these devices will be rather small. And in some cases also they will be so small that they won't have the ability to connect directly to the backend or to the cloud, which means that there will be a gateway in the middle. And typically, that's a slightly larger system that specializes in establishing the communication channels and maybe do a bit of pre-processing in the meantime. So what we can ask here is, what is new when you do these kind of deployments, when you move into a deployment in which you have actually connected devices here? So what changes from a traditional system with the backend and users are the devices, of course. There are many of these devices. And many, in some cases, like talking with utilities, may mean millions. And in terms of management, this can lead to interesting challenges. Then, in many cases, for many use cases, the devices that we're talking about here are at the heart of your business. They are really something that defines the business you're doing. So the meters for an electric company are important because they are really the interface with a customer. So what that means is that for the customer, in many cases, the devices, they are you. They are the company who actually owns the device. They are the representatives of this company. And it's important that these devices work correctly there. However, of course, if you compare these devices to the other elements that make your information system, you will have very little control to these devices. It's not easy to reach to them at all times. You may be able to reach to them sometimes. In some cases, it may be even difficult at all times, especially if they are the customer's premises, behind firewalls, etc. So they may come back to you sometimes, but you may have some trouble to actually manage these things. And since we're talking about security here, we can also look at what kind of new risks are introduced. The main risk here is that you have a new entry point or millions of new entry points to your system. So that means that there's a new way to reach out to your system and maybe attack it in some way. So there are at least two big categories of attacks that can be made. There can be some attacks on the device, either by tampering with the device or even by building a fake one. Also to attack the link between the device and the backend. in which you can steal the customer's information or inject false information. And of course, we have to mix that with the fact that these devices still are very much representing you, and they are hard to control. So that's why the security needs to be considered seriously at the beginning before the devices are deployed. So let's look a little bit about the typical security thing that we'll have to do here. The security we're talking about is really about the resistance to attacks. So we can have many definitions, but here we're focusing on that and defining an attack as an action that is intended to abuse the system for the benefit of the attacker rather than the benefit of the device's owner. And when you do think about security as resistance to attacks, we need to have a different frame of mind, which is the users are important. We don't want to disrupt what the user is doing, but it's important also to understand what an attacker may want. Because the motivations of the attacker are going to be important in understanding what kind of countermeasures are needed. If you're going to do some kind of a media player, your attacker may be the customer himself trying to go around DRM. If you're more into critical infrastructure, you may have to deal with potential terrorism actions. So you don't have the same way of acting against these kind of attackers. You don't do the same thing against a standard user and against a potential terrorist threat. So this is something we need to do. And if we think about it also about the vulnerabilities, this is something that we need to think not necessarily as bugs. If we look at the vulnerabilities that make the news on systems that have been deployed for years and that have been used by millions or hundreds of millions of users, they are very often related to more or less bugs. But if we think about systems that are new, in many cases, the vulnerabilities are not related to an implementation bug, but they're related to an actual feature, which means that something in the system or in the device has been designed to work in a certain way. And in that design, there is a vulnerability. And these kind of things, when it happens, can be very hard to fix. Because if the specification is wrong of the device, if there is something that actually you do and you shouldn't do, then fixing it may be harder. And in some cases, it may actually make the application just impossible, make it impossible to have the application do what it's supposed to do. So if we look about the requirements here, about the security, the ones that we see most often on the devices, the first thing, of course, is safety, and we have privacy, regulation, access control, and accountability. Those are the things that we see most often as being mentioned here. That are not, very fun things, except that, like always, when we think about security, we have to make sure that all of these things remain true even under attack. And under attack for a device, you may not be very much aware that there is an attack. At least your backend may not be aware at all that there is something happening. So you need to have some local security features here. So in terms of safety, doing what you're supposed to do means that even in the case of attack, you need either to have an application that keeps working or that fails gracefully in a way that is planned in the specification. And so again, this means that you have to consider what kind of attacks can occur, which will lead to what kind of failures, and then you can figure out how to deal with these different failures. And when we talk about privacy, here we're not talking about maybe you deciding to sell your customers' data, but more about somebody else who would steal the data and sell it. So if you have defined a privacy policy, what security people will care about is making sure that the policy is applied. Now, defining the policy and the ethics, whatever, that's business consideration. That happens before that. Then the regulation. So regulation has a bad reputation because it forces you to actually abide to some rules that were defined by somebody. And in many cases, these rules may look obscure and not very useful. But if you think about it, in terms of what the regulation is about. In many cases, it is a consequence of people thinking about what may happen. So if you look, for instance, what the various PCI recommendations for which there are some regulations and that needs to that are really needed for every system that works with payment data, we have defined these things over years and years of experience. So for a newcomer in the industry, it is actually an opportunity to get access to a lot of knowledge that is difficult to get access to. Then, access control. This is something where there's not much. We said we just want to restrict access to authorized persons. And accountability, this is more of a meta property, but we want to make sure that the other property, the safety, privacy, regulation, we have some traceability about how we actually apply that, so that we can prove to the outside world that we're actually doing the right things to protect the systems for these things. So in order to meet these requirements, of course, we have a few security functions. So I'll go very rapidly about that. You can read full books about every one of these things. So you have the data protection, where you can protect confidentiality and integrity. You're going to have authentication, authorization, where you can start with passwords, but if you're on a machine, it's going to be maybe different. It's going to be more cryptography based, because the machine doesn't know passwords, or at least it's better that a device is not authenticating with passwords. Authorization is about access rights. So this is something that is very important, making sure that it's always the right person accessing to the device. And you have the logging and auditing. This is extremely important, all the security log. In case of an attack, if you have good logging capabilities, that means that once you know that something has happened, it's fairly easy to understand where the problem comes from and at least find some immediate countermeasures. If there is no log, then it may take a long time to just figure out how the attack happened. And when there are logs, we also need to be careful that the access to these logs will contain, in many cases, a lot of sensitive information is restrictive also to auditors. Then we have provisioning. So provisioning is not necessarily directly related to security, but in devices, it's important to understand that having the ability to have a system upgrade or an application upgrade is one way to deal with some kind of a vulnerability in the device. And the main problem that we may face here is that depending on where the vulnerability is, it's really difficult to make sure that the provisioning system on the device will keep operating normally, so that it will still be possible to perform the required updates. So this is something that is important to think about. And then we have the software protection, making sure that the code is not modified. The code integrity with signatures, with code verification, like is done on Java with the bytecode verification, and some runtime integrity, when that's possible. So let's look at smart metering now, so we get some kind of a real-life example. The reason for most people to move to smart meters, there are two main reasons. The first one is to have better data collection. So we want to have less manpower and maybe more accurate information, because there will not be anybody having to type in numbers all day. There's also the idea of enabling the smart grid, the big data, so you get an enormous amount of data about the customer's consumption of whatever you're metering, so you can get better control of the grid and also get some feedback to users. So if you want to modify their habits for consumption, this is something where it's important to get this data so that you can provide some feedback to these users. But there are some consequences in there. If there are less manpower, then it means that in some cases fraud detection will be difficult. I mean, if somebody just puts a cable that goes around the electric meter, well, it's not that easy to do, but if there is somebody that comes to look at the meter once every few months, they will see this thing. If nobody ever comes to look at the meter, some cheaters may go away for a long time before anything is detected. Another thing is that, of course, because there's a lot of data flowing in and out of the meters, there was a possibility here of injecting wrong data or looking at private consumer data. So if you look at one private consumer data, you get easily some information possibly about this person has not been around for 2 days. Now if you get the same information for an entire neighborhood, you can map the neighborhood have a map of who's in town, who's not in town, and sell that to people who could be interested in visiting empty houses. So we have to be careful that these leaks don't happen. So if you look into more details about the smart metering, if you have a meter, it's going to be owned by a utility company, or depending on the countries, there are different configurations, but it's usually owned by the company who's going to bill you for the electricity. The obvious thing is that this company usually is in charge of the maintenance, and one of their big characteristics is going to be that the lifetime needs to be greater than 10 years. They don't want to change the meters every time. So it's very hard with smart meters because this is new technology today, and they have to get it right the first time and not have to change it too often. The same thing, they don't want to have human intervention. If you have 10 million meters and you need to visit every one of them, the cost is staggering. So you have to be very careful that these kind of things don't happen. So what they're looking at here is having a meter that is tamper resistant. We have always had some requirements like this for meters, but we really need to make sure that the meter can't be too much tampered with. The good part for people who sell the meters is that usually the price sensitivity for this is quite limited, which means that it's unlikely that utilities will go straight for the cheapest meter around. They will more look at the functionality and make sure that they get the best combination of good price and good capability. So there's a possibility here definitely to differentiate on these kind of things. And the last thing also is that the raw data here is privacy sensitive, so we have to be careful about this data. So if we think about it on threats, and we'll look at them maybe with more detail. On the device, we can tamper with the data collection, we can tamper with the collected data, and between the device and the backend, we can insert fake devices, modify transferred data, or steal the transferred data. So let's look maybe with more detail. So in terms of data collection, with a standard meter, what we want to achieve usually is tamper evidence, which means that if somebody tampers with your meter, what we need to ensure is that when somebody comes, an employee comes to look at the meter, it will notice immediately that something is wrong. So that's the evidence. If it gets tampered with, the meter will just, if you open it, it will never close correctly, and this is visible. If nobody visits the meter, you have to move from tamper evidence to tamper resistance, which is a bit stronger property, where you need to make sure that the meter actually resists to tampering until something up to a reasonable amount of tampering, and then when it's unreasonable, it just breaks down. So this is a bit more difficult to achieve, particularly because you want to make sure that a lot of things remain impossible here. Then about data storage, this is a completely new issue. In a standard meter, there is no storage of data. There is one value that keeps being updated, but that's about it. In a smart meter, usually you can have to store some data, at least temporarily, between two data collections. So you're going to need to make sure that this data is not modified and that this data is not leaked. So integrity and confidentiality issues. Another problem is we can have fake devices. I'm not completely sure why somebody will have a fake meter. That could be just to inject fake data in the big data model and make somebody believe that there is more consumption in the area or something like that. But I'm sure that there is a use case for that somewhere. So we need to make sure that there is a correct authentication of the devices that we're talking to. And the same thing on the other way. The device needs to make sure that it's talking to the right server. So the device not completely control the entire communication link, which means that the authentication here must be mutual between the meter and the backend. And the last one is the man in the middle, which is that somebody can come and look at what is happening or modify the communication, which means that here we need a secure channel, once again, that protects both in integrity and confidentiality. So in order to do that, we're going to have to design the security in the meters. So this is something that meter companies know how to do. A meter has always been sensitive. Now there's a little bit more sensitivity. So as I said, we need to tamper-proof the device. That means going maybe one step higher in terms of what the device can resist to. So, for instance, if we think about the point-of-sale terminals, in many cases, the point-of-sale terminals, in particular those that handle the EMV transactions with chip cards, they contain secrets. And in order to protect these secrets, the whole terminal is lined with a mesh, and if anything touches this, if you try to drill or open it in some way, all the keys will be gone instantly. So once again, this is about tamper-proofing, which means that you make the device like non-working if anything goes really wrong. We also need to have a protocol that's secure enough. These protocols exist. TLS provides everything we need from the authentication to the secure channel. To use a good software stack. So, well, we're on a Java conference, so we can assume that Java ME, for instance, is definitely a good choice for a meter. And the last thing is about adding a secure element. So the idea about adding a secure element here is that you can get a really tamper-resistant hardware that was always designed for that, and that also, because the piece of hardware that you get in a secure element is very small, the software on it is very small. So it's possible to get to level of certifications that are very difficult to reach with things like even like a smart meter, and of course even more for something that is larger than that. So let's try to see how we can use secure elements to actually build trust on devices. So I will focus on 3 ways in which secure elements can be used to actually secure a device. The first one is about basically securely storing some credentials or important secrets. And here I'll take an example, the satellite TV cards. The second one is using secure elements as a backend proxy, which is representing a service provider in the device. And the example we'll take here is a SIM card. And finally, we can use a secure element as a device root of trust. So you can build the trust that you need in your device, starting from the secure element. And the example of this is the TPM, which is the base of the trusted computing thing. So the first example is about satellite TV. So satellite TV is interesting for hackers because it is broadcast. So the same signal goes to everybody. So you can catch a signal, and if you can catch it, somebody else can catch it, and if there is just a simple device to just decode the signal, some, I would say, hacker or bad guy somewhere can decide that they will sell a device, and then that will be much cheaper than the original thing sold by the satellite provider. So of course, the people who provide the content have understood that, and the content now is encrypted. So you need to have the right key on your device. But the problem here is that it doesn't change the basic property. The content is broadcast, which means that it's still the exact same content getting to everybody, which means it's the same key getting to everybody. So if the bad guys are able to get a single copy of a key, they can duplicate it, and their business model is on again. So that's why this key needs some good level of protection. So that's why we can put that in a secure element. That's actually the original rationale behind building secure elements is to protect some sensitive assets. It started in the 80s with real assets in phone cards. Phone cards, you had units of communications that would be burnt one after the other. And the idea was that they were protected in a card and difficult to reach there. So of course, that had some limits, and very rapidly we've seen the replacement of these real assets with things that are more based on cryptography. So usually the assets that are most often protected in secure elements today are cryptographic keys. And here, once again, this is tamper resistance is important. And when we're talking about smart cards or secure elements, the level of tamper resistance we get is that you have a very small chip that's embedded in some special glue with a lot of detectors, light detectors and temperature detectors, etc. So if anything goes wrong, this thing will kind of self-destruct itself. So the idea is that attacking a card requires a lot of effort, and it requires also a lot of equipment. So once again, the idea is always the same when we introduce a new security measure, is to make the price for the bad guys higher so that their business model doesn't work anymore. So when you have a secure element here, the guarantee you get is that your keys are better protected. They are in the security of the device, which means that the bad guys are maybe won't have access to the keys anymore, and that destroys their business model. So if we think about how this works today, a lot of set-top boxes actually use smart cards. They've been using them for years. And there's been a lot of a race, I would say an arms race between the content providers and the hackers. So the original cards, of course, eventually were broken, so they were replaced with more complicated things. And basically, there's always chasing each other. So these days, I think there's an edge in favor of the content provider industry, because they have now more power to diversify the keys, which makes it very much more difficult for hackers to have a business model that will actually work. And something important when you think about also these secure elements is that they're not just storing secrets, it's not just protecting them by storing them, it's also the fact that if you have a very important key, it never gets out of the card. Some computations are done on the card. You can have, obviously a Java virtual machine on these cards. So the core secrets never get out. So it means you have diversified keys going out, but the core secrets never get out and are very hard to remove from there. So the second use case is mobile telephony. So here we have a network operator that provides network infrastructure to its customers. So the customers are allowed to connect to the network with their own device. So the network doesn't own the device. And of course, without security, attackers get there and, for instance, they insert a fake device which is configured to work as a copy of a real one. And what that does is that you get somebody that makes phone calls on behalf, or being paid by somebody else. So there are other kinds of attacks, but this one has been one that has been key to the design of the SIM cards. So here, the idea is to add a secure element on the device that will be removable, but it's mostly used to communicate with the backend. And the SIM card is owned by actually the network provider, and it's not really made to make the device more secure, but it's really acting as a representative of the operator on the device, which means that if a device is equipped with a SIM card that is related to a given operator, you can connect to that operator's network. And the operator doesn't have to figure out if they trust or not the device. And that is very important in areas where the service provider doesn't have any control over what kind of devices are being used. And for instance, this is important also if you want to have something like a bring your own device thing, which is exactly an extension of this model, where you need to have a smaller subsystem on the device that you can trust and that will allow, for instance, a corporation to use its employees' devices for doing some operations that require some trust. This is exactly the same kind of model we're talking about here. So the last thing is about using the secure element as a device root of trust. The idea here is to protect the device integrity. So I have not put a name of that device. It can be just about anything. There are at least two ways in which a device can be compromised. One is directly by the end user, wants to change the software, and another one would be through an external network attack, if somebody actually tries to tamper with the device from the outside. If you're thinking about a business model in which you have many devices that are connected to a backend, this is actually very dangerous because the consequences are very hard to understand, because the modification, they may be big, but they also may be on details. So if you have a meter and the meter only meters 9 times out of 10, you just get a 10% discount. That may be very hard to detect. So also, because there's limited access to the device, fixing it directly on the device can be difficult. And in some cases, if there has been some compromission of the device, the remote access can be disabled. So of course, if there is a good level of tamper resistance, disabling any remote access will most likely lead to detection of the problem, but this is also hard to organize. So here the solution that is being used today in the trusted computing is to use what they call a TPM, or Trusted Platform Module, as a root of trust. So the idea here is that we start from a secure element which has all the proper security certifications, and it has two additional properties, or different properties from the other ones we've been talking about. The first one is that instead of being tamper resistant, it's now tamper evident again, because we have here a maybe $1 little piece of equipment that controls, or at least controls, the integrity of a much larger device. And if there is a problem with this little TPM, we don't want the big device to be completely deactivated. We just want anybody who uses the device to be aware that the TPM has detected that something went wrong. So that's what we want to know. The other one is hardware integration. It's very important when you use something that is going to verify the integrity of a device that it starts first. The idea is that when you boot, for instance, a PC which is equipped with a TPM, when you turn it on, the first thing that happens is that the TPM gets powered, which allows it, for instance, to start verifying the kernel. And that and that is the main use case for a TPM, is actually the secure boot, where the trusted module is going to verify the kernel, and then the kernel starts, possibly verifies the OS, which starts, etc., etc. So you have layers of trust. So you have the most trusted thing in the middle, and then as you go out, you have more and more complexity, and maybe more and more problems also. But another important thing about TPM is the fact that there's a possibility to have remote attestation, which means it's not only local, there's also potentially a link with an external server. The idea being that once you have booted your machine with the proper boot sequence, that the TPM can provide an attestation to the outside. Yes, this system has booted correctly. It's been in this configuration with that, and I can guarantee it's been done right. And of course, this is signed with a key that can be recognized, so that the outside backend can ensure, before to perform any kind of transaction, that the state of the machine is correct. So to recap on these three ways to use the secure elements, if you think about the secure store, the value here is mostly for the service providers. It is very well suited for models that are unconnected, in which the device is either never connected to the outside, well, in which case it may not be fit very well in our original model, or in which the device is connected irregularly. Sometimes it's connected, but most of the time it is not. And the focus here is on the local security and really trying to figure out how we can make it more difficult to steal some secrets directly or modify the integrity of the device there. In terms of using the secure element as a backend proxy, once again, the value is mostly for a service provider, and this is particularly well suited to models in which we are connected in most of the cases, because there's going to be some end-to-end communication, and this end-to-end communication is basically independent of the device itself. And finally, the third thing is the device root of trust, in which the secure element brings, this time, the value mostly to the device providers, because it can improve the security of the device in any kind of application models, because it works on guaranteeing the integrity of the device. And if we get back to the smart meter, we can try to figure out what kind of secure element model is needed there. Well, it's mostly a backend proxy, because the main use of the smart meter is going to be here about authentication and secure channel. That's the main thing that it is used for, making sure that every time you connect to the backend proxy, it's done correctly. And there is also some local data management. And this local data management is done really on behalf of the service provider. But if we think about this is mostly unconnected. This is between two connections. We're going to accumulate data and protect it, which makes it closer to a secure store, in particular in models where there is a local interface to which the customer can get information from the meter directly at any time. And finally, although I'm not sure it's used like that in many secure elements, in many meters today, it could be interesting to have a root of trust, once again to protect the integrity of the meter itself against attacks. So if we move beyond the meters here, or the examples we had, so embedded systems use a lot of security subsystems like that, and there are a few examples that I can bring here. The first one is anything that uses some kinds of smart cards. So we've seen some of them. So the mobile phones, a lot of them use SIM cards, billions of them every year. The point-of-sale terminals store their secrets also on a removable smart cards that is owned by the payment processor. And once again, on the media players, we get some smart cards for DRM, in particular for broadcast content. And then we have what we call maybe the embedded secure elements, in which instead of having a removable card, there is one secure microcontroller that is actually soldered onto the device. So here we have the wireless modules, so you can see for instance, what Centurion has been building there, in which in most cases there is a SIM card for performing the authentications. There are also such secure elements in NFC phones that do the mobile payment, because the mobile payment is secured by a secure element. And once again, in smart meters, it is mandatory in some countries like Germany to actually have a secure element in the meter to protect the data. And there are also some models in which, for instance, prepaid meters where there is some stored value, where most of the reference design actually include a secure element in which the stored value will be stored and protected throughout its use. Another kind of security subsystem that we're starting to see is what we call a trusted execution environment. And This one is something that runs mostly on, say, on the main processor, and that basically introduces some kind of safe execution mode or trusted execution mode, in which we can be guaranteed, for instance, that at startup we first start in that mode and that it gets some control over some pieces of the mobile device. So we're starting to see that, particularly on high-end mobile devices, smartphones, tablets. And the main use cases today are device integrity. So there's been a few devices, for instance, from Motorola, in which it was almost impossible to change anything in the software. And some hackers would be complaining about it. And that's because they really activated this feature without any way to go around it. And there have been also some uses around DRM. So for instance, if you want to use Netflix on an Android device and have HD content, you're going to need to have a device in which the TEE is actually working and where Netflix has downloaded their DRM. And finally, the TPM. So that's a trusted platform module, which is used mostly in PC-like configuration. So this we see, for instance, in ATMs, and in many cases. So a lot of ATMs verify the integrity before they start running, because this is something that is easy to do and that allows them to get a good level of protection. And same thing, we have some media players, which are pretty large machine on which for a DRM use case, there is also some control of the system integrity. So we get to where Java is in here. So Java is in a lot of smart cards and secure elements. Actually, in all the examples I've given here, there are some significant market shares for Java card. So on SIM cards, on EMV payments, both on POS and on cards, there are a lot of them here. The system has been around for a while. It's fairly stable. Now we're seeing more and more secure elements, and this is something that is actually just appearing. Now we have secure microcontrollers with standard IOs that can be easily integrated into any kind of design of embedded devices. So this is something that is starting to be deployed more widely, and we expect it to grow significantly over the next year. So in terms of the TE and TPM, so right now they're more closed systems, but we are seeing them opening rapidly for the TE, and it's more, I would say, starting to happen for the TPM, and we're kind of monitoring that closely from Java Card. So just to give you very small information about Java Card, it's a very small subset of Java. It's complemented with very specific APIs for crypto, protecting passwords or whatever credentials you may want to store. The interesting part about it, it has been designed from scratch as a multi-tenant architecture with applications that are strongly firewalled, because the idea is that in a single smart card you can get applications from people who don't trust each other. If you think about mobile payment, you're going to have applications from for instance, a network operator and a bank in the same card. And these people, they don't trust each other, they don't like each other. But it took them between 5 and 10 years to find a business model, but the technical solution has been ready for much longer than that. We also get with dynamic application management, and there's a whole ecosystem about managing applications for Java Card. So in particular about embedded secure elements. Now we're seeing that with something called TSM, so it's Trusted Service Managers. And as I said before, it's now available on embeddable secure microcontrollers. And also, if you are having a smart card, there are some APIs available in Java to communicate with these elements. So JSR 177, also called SATSA, provides access to secure element from any embedded device that you can have. So you can have this if you have a secure element. And we also have JSR 257, which is used if there is a contactless interface, but it's more of a, let's say, it's a small use case in here. So just try to conclude here on recapping the important things about the edge to enterprise security, I would like to really put some emphasis on the fact that it's very important, in particular when designing new devices, to include security in the entire process from the very beginning. Because this is where some terrible mistakes can be made just by not thinking about it. So the first thing is to identify the security requirements, what kind of security features can be required on the edge devices, maybe more importantly, what kind of attacks need to be considered. And this is very hard. This is something where we get surprises every day. A lot of people think about some obvious attacks and forget about some maybe even more obvious, but not from the same point of view. So this is something that needs, I would say, some empathy with the bad guys, at least to be able to think like a hacker or a bad guy to be able to do that. And another one is about what kind of assurance level is required or will be required. And this is also very important because this is basically how much are you going to need to prove that your security is correct. Will you need to have a security certification? Well, if you need, for instance, a common criteria security certification, you know that you're going to need to add at least 6 months of delay and a few $100,000 of budget. So this is something very important to know at the beginning. If you learn it midway through the project, it's not good news. And then the other thing is to really try to identify the security functions and to think about them as a security subsystem. If you're, of course, the security is more or less everywhere in any kind of your system, but there are usually some security functions that are dedicated to that, and it's very important to identify them so that you can spend more effort in terms of testing. So, for instance, this may be the kind of functions where you want to do different kinds of testing with more static analysis, more fuzzing, more actions that would more simulate what a hacker could be able to do. And then when you go for the implementation, there's a choice about where you're going to put this security subsystem. So of course the easiest and traditional way is to put it in the main code. So if you have isolated it, it could be a few classes, it can be a package that deals with this security. Of course here the assurance level you get is minimal. It's really related to the amount of it, maybe testing or specific testing you can put to this. But it's already much better than just not identifying and having your security functions being randomly put anywhere in your code without any kind of specific treatment to them. Of course, being in the secure element thing, I will consider using a dedicated secure element. What that brings you is really a way to improve the traceability because it is a separate secure element. You know that every use of your main security functions is going to involve some kind of exchange between your main system and the secure element, and that's much more traceable. And also you can reach the highest possible assurance level. Some smart cards have been certified to the highest level for common criteria, which is fully formally proven. So these kind of things can go as high as you need. And of course what you get is better protection for your assets and better tamper resistance. It has a cost. I mean, these things, they depending on how many you want to buy, or it's going to be a few cents, or maybe a dollar for the most expensive. But this is not the I would say not necessarily extremely expensive in terms of adding such a secure element here. And of course, we know that more options are becoming available. Trusted computing is already available as really one way to do a few more or less fixed applications. It's now starting to open. There's also the trusted execution environments that are showing up. The entire Java card team we're clearly following these initiatives to find out exactly how we can extend this to all of these security subsystems, and we believe that we can do that in the future. But to conclude, I would say that one thing that is important here is really not to forget the very basics of the security engineering. The security engineering is mostly like an insurance against breaches. A breach can be extremely costly. We've seen with compliance issue some kind of payment processors. There were nice payment processors that they have a PCI issue. They have a breach. Then Visa, MasterCard realize that they don't comply to PCI, remove the certification. Then they lose their customers, and within 3 months they're bankrupt. So, of course, this is an extreme case, but it's always very difficult to figure out how much a breach can cost, depending on what kind of data will be compromised. Same thing in the health environment. There's going to be some HIPAA compliance. I doubt it's going to be much easier, and there's going to be some problems there, and going to be many embedded devices that will need to comply to these things. And the very last thing is that some attacks happen and devices will be targeted. A lot of people who are doing embedded devices today are not thinking about security. I've had some friends who are actually working on attacks. They attacked pacemakers, and they decided that they would not publish their results because it was so easy to do it that they just don't want to give any information to anybody, because attacking a pacemaker is potentially killing somebody. So you have to be careful with that. And these people today, they don't use secure communication or authentication. So you have to be careful, and this is not going to be possible in a few years from now. So we know that the attacks today, they're moving from Windows only, what it was before, because of course 90% of things were Windows, to we've seen that Mac OS is getting some attacks. The mobile devices are getting more and more. And if you're putting some devices on the market, you can be wildly successful. And if you are wildly successful, one bonus that you will most likely get is that hackers will get some interest in your devices. And that's when you have to be ready here. Thank you.